Started with the session now. Okay, so before we jump into what ROS is, I would like to give you a better understanding about something called a robotic process cycle, which is, the foundation for pretty much the entirety of robotics. So all robots that we see around us, it'll be around 20 minutes, 25 minutes at max. And don't call me sir and all. I'm just a student. Don't call me sir and all. So most 99% of the robots that we build are based on this thing called a robotic process cycle, which consists of three things, as you can see: sense, think, and action. So what does sense include? Sense includes all the sensors, the cameras, the lasers that we use in our robots. All these things come under the factor called sense. Then think. The part of a robot which we implement AI models in, machine learning models in, and signal processing, these consist of the thinking part of the robot. And the action. The action includes the motors, the actuators, all the stuff comes under action. So this is how a robot basically works. So it senses changes and values around in its environment, sense it to think, that is to our AI models and our machine learning models to process that raw information, and based on the outcome of this processed information we jump into action, whatever action needs to be performed. So why am I talking about robotic process cycle before I jump into ROS? Let me give you a quick short example. Water level sensor, for example. So those who would have studied in IoT would have known something called a water level sensor. So basically what that sensor does is it helps you to detect water level in a container. So let us say I have a system to check the water level in my container, in my tank for example. So I have a motor which switches off the pump, and I have a water level sensor which detects the water level for my system. So one sensor, one motor, very easy to implement. You just code the sensor program in your Arduino IDE for example, and then you run the code and your sensor works perfectly fine. So what if I had to do the same thing for an entire apartment, for example? 100 houses in an apartment. I have 100 water level sensors, and I have 100 motors to run. Do you think it is practically possible for me to code each and every sensor, each and every motor to stop at when water reaches a certain level? Is that possible? Practically not. So that's where something like a ROS steps in. So to improve on implementing the practicality of these sensors, for example, is where ROS jumps in. So let's see what ROS is. So what actually is ROS? ROS stands for Robotics Operating System. Let me repeat myself. Robotics Operating System. It's an open source meta operating software. So it is not exactly an entire operating system, but a meta operating system. I'll explain it to you why it is a meta operating system when we talk about the architecture of ROS. But this basically helps us in the lower level of device control. As I said, it helps you to control sensors, it helps you to communication between these two sensors. But what ROS is not, it's not a programming language, or it is not a library, and it is not an IDE. It is a meta operating system, which we'll talk about how we use ROS further in the next few minutes. But its main purpose is to implement device control at the lower level as in the sensors and the hardware level is what we call the lower level. So here I've linked the ROS documentation, so I'll share the PPT later. You can just read through it, because ROS is an open source community, so people contribute, and it keeps on improving day by day. So what so that's so documentation, reading through the documentation of ROS will help you get a much better understanding on how you can implement ROS and so on. So how do we use this ROS? We base it on a Linux operating system, and along with it we have few more things which I'll talk about when we talk about the architecture of ROS. Okay, so I told you so much about ROS, and you might be wondering right now that why am I talking about ROS, and why not simply use Raspberry Pi and Arduino. So in that case, let's go through an example. I am creating a robot which I want to use both Arduino and Raspberry Pi. So what I'm going to do is I'm going to use an ultrasonic sensor so that I can do obstacle detection. So what we do using ultrasonic sensor is we send waves and we receive back waves. So if in case it hits an obstacle, we will receive some distance, we'll receive some signal which will show that there is an object in front of the sensor. So best, ultrasonic sensor is best run using Arduino. So what do? I use Arduino and I'm going to use an ultrasonic sensor so that I can detect the obstacle in front of me. And I want to do something else as well. So the AI students who either have learned or are going to learn, you would have learned about machine learning techniques or algorithms which are used for something called object detection. So based on some physical properties of the object, you detect what it is, a cube or a square or a sphere and so on. So what I'm going to do is I'm going to set up a camera with the Raspberry Pi. So I'm going to set up a camera with the Raspberry Pi, and I'm going to use an ultrasonic sensor with an Arduino. But this is where the problem comes. I want both these information onto one. So what do? I have to use something so that I can control both the Arduino and the Raspberry Pi simultaneously. For that, I'll have to use something called a master device. So what is the use of a master device? It'll help me control whether if I want to detect if there is an obstacle in front of me or not using an Arduino, or do I want to detect the type of object in front of me using the camera and the Raspberry Pi. So for that master device, again I have to use something like an Arduino or a Raspberry Pi to control it. So imagine, for such a simple task such as obstacle detection and obstacle classification, I have to use three microcontrollers, which is either two Raspberry Pis and one Arduino, or two Arduinos and a Raspberry Pi, and I have to set up communication links between all these three, so that all the data which we collect from the sensor goes to this master device. Imagine the pain that we have to go through to just make this model work. And right now we are thinking about self-driving cars, and which employs so many number of sensors. It has a camera for the front, it has camera for the sides, it has camera for say sign detection, it has a camera for signal detection, then you have cameras at the back, rear view cameras, and then you have sensors to detect if you're on a path or not. So just imagine we had to use the same structure that we used for our robot to build in a self-driving system. Do you think it is practically possible to build a self-driving car itself? No, it is if we had to do it in that way, then it would be practically impossible to build a self-driving car. That's where ROS steps in. What ROS does is it allows you to communicate and set up links between devices without having too much cost, or let's just say that you don't have to reprogram everything again and again and again, and you don't have to ensure that the communication links between the devices are compatible because you're using different hardware. And let me also tell you that we can't use ROS independently. I can't just install ROS in a robot and expect it to collect data from sensors. No, that's not how it actually works. We need both these things so that a robot can function smoothly. That's what gets to me to my next point is I'll explain you how exactly does ROS work. So these nodes 1 and 2, these nodes. So before explaining the architecture, we use C++ or Python to program our nodes. What exactly are nodes? Nodes tell you what exactly a robot should do. For example, a simple two-wheel robot. I have two motors attached to my robot. So one node can simply be a command or a program written in C++ or Python saying that the robot should move forward and the motor should be on. Basic, simple. So what nodes exactly does is what we want to do with the robot. I want to make the robot move forward, or I want the sensor to get a reading, or I want the robot to display something on the output. I code that into my nodes using C++ or Python. And the main factor in ROS is there is something called a ROS master, which basically controls every single node. So for a node to function in your entire robot system, it has to be connected to the ROS master. So the ROS master will help us in communication between these two nodes, and it doesn't matter. For example, I write node 1 which is in a C++ code. I write my C++ code for my ultrasonic sensor, for example, and I write my node 2 which is in Python, and I use certain libraries in Python to run my camera. It is not necessary that both nodes have to be in Python or in C++. Doesn't matter. The language of programming your node doesn't matter. You can still use the same information that you get from node 1 and 2, and you can perform your task easily because of ROS master. And how exactly does the ROS master do this? Using something called the client libraries. So ROS-PY and ROS-CPP. It ensures that the programs which are written in C++ are understood and translated into something which the programs written in Python can also understand. That's how the ROS master works. And as I said, ROS's main purpose of introduction for ROS was easier communication between the nodes, for example, in this case. So TCP, UDP, ROS. Those who would have studied in computer networks, you would have heard of this term called TCP, UDP, which is Transmission Control Protocol and User Datagram Protocol. This is not, and for those of you who don't know, don't worry. It's just simple set of rules which should be followed for the data to for communication of data between node 1 and node 2. Simple. This is just a set of rules, and the same rules which are being utilized by ROS is called TCP ROS and UDP ROS. Simple. And last part, but the most important part for ROS in its architecture is a base Linux system. So why do I remember I called ROS as a meta operating system here, and it is not exactly an operating system. Why did I say that? That's because it is based on Linux. And why do I need need Linux? Because ROS does not have all the features that an operating system does. That is why it is called a meta operating system. So we have to host ROS in a Linux system, and using that Linux terminal, we'll be executing all our tasks and perform whatever work we need to do with ROS will be done in that Linux environment. So how exactly is ROS going to work? We're going to have a Linux terminal which will run the basic requirements of your ROS libraries, and you will be programming your nodes using C++ and Python. To dive more deep into this, there is something called topics, ROS services, ROS messages. We'll all won't be talking about that in this session, but if you guys are interested and want to learn more about this, do let us know. We'll take it forward. Okay, what after this? So what else does ROS give me with this? As I said, as I explained to you point by point, these are all the things that we can do with ROS. We can do process management, inter-process communication, device drivers, which is basically communication. Tools, this I'll talk about in the next slide. Simulation, visualization, and you also can use ROS for control, your planning, planning, perception, all this we'll talk about in the next slide. And ecosystem, your documentation, your tutorials, your packages. It's basically a more organized way of creating your robots. And visualization and simulation tools. This is where ROS gives you an added advantage, gives you another major added advantage over just using an Arduino or a Raspberry Pi, which is the simulation and the visualization tools that you get along with ROS. So we have something called a gazebo and an RViz, which I'll show you demonstrations later. But not only can you program nodes, but you can also visualize and check how your robots will actually behave. So what you can do in something like a gazebo is you can deploy robots in environments, and you can make sure, and you can run your nodes, and you can see how your robot will actually behave in the real world environment. And for example, for people like me, I can't go out there and outright buy hardware and build robots because it's way too expensive. So for someone like me, what I do is just deploy robots. You deploy pre-built robots, for example, in the gazebo environment, and I'll run my code and I'll see how my code is actually working and how I can improve it. So for example, I'll be showing something called a TurtleBot 3 in a few minutes, and I'll show you how we can actually deploy it. And RViz, what is RViz? You let's take an example for there's something called SLAM, simultaneous local and mapping, and there's something called navigation. So what we do is the robot moves around in the room and it helps you map the room using sensors. So something for that, you want to know how exactly and how accurate is your robot in mapping the room. So something for that, for example, RViz is very useful to see what sensor readings that your robot is getting, and is it actually getting the desired output for the code that you've written and for the nodes that you've written. Does it actually help you or not? So that was about the simulation and visualization tools, and let's jump to something called ROS versus ROS2. So I don't know about you guys, but I have been following the robotics market as of now for quite some time now, and ROS2 is something which is currently in market right now, and it's going to be the future of ROS. Why is it the future of ROS? As I said, in ROS1 we used something called a master, ROS master. So what we had to do was connect every single node in our application to one single ROS master, so which exposes us to more chances of failure. So if the ROS master of your program in a robot fails, no matter how good your nodes are, it's not going to work. So a simple thing such as a failure of the ROS master can affect the entire process cycle of your robot. So that's where ROS2 steps in, and ROS2 gives you distributed processing. So you don't have to rely on a ROS master to run your nodes. Also, one more key point is that ROS initially was an open source library. So all the security, security today is becoming one of the core concerns of not only just robotics but every single field. So ROS whatever was developed by the open source community. So every, like things like security programs or added security layers, for example, those things are built by the open source community. But now, since ROS 2 is coming up, security is one of the very, 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 very important factors for ROS 2 to be, a successful hit after ROS. And last but not the least, as I said, ROS is based on the Linux environment. So that again is a constraint because it restricts the developers to use a Linux system. I myself switched from a Windows system to Linux system so that I can do more of ROS and with more computational power and so on. But what ROS 2 will help you, will allow you to do is run it on any other base operating system. So you can run it on Linux, Windows, Mac, RTOS, anything you can run it on. So the point being, although ROS 2 is still in development, it's not like 100% as error free, and the community is still working on it. But by 2024, 2025, ROS 2 should be like it will come up. It will be the robotics as operating system in use. So before I jump into simulations, is there any doubts or any questions you would like to ask? If there isn't any, then I'll show you simulations. Okay, then I'm assuming there's no doubts. Okay, let me just share my screen again. Okay, I hope it is visible right now. Okay, so let's talk about the ROS master, which I told you first. So this is something which we run, which is called a ROS core. So basically this is used to set up the ROS master. So what I'm doing here is I've started the ROS server. This is my unique ROS master ID which I'm using right now. Then ROS noetic. What is noetic? Noetic is basically the version of ROS that I'm going to be using. So I run my ROS on a Linux terminal. As I said, everything that we do, we run it on Linux. So today I'll be demonstrating something called Turtle Sim, which we use to learn the concepts of ROS. So as I mentioned previously, something like called ROS topics, ROS messages, ROS services, all these things we learn using something called a Turtle Sim. I won't be teaching the concepts today, but I'll be demonstrating to you on how I run the Turtle Sim, for example. So I use a command called ROS run, and I'm going to be running something from the package called Turtle Sim. As I said, this is the package. So I use the command called ROS run, which is the command which we use to run packages or nodes. ROS run, Turtle Sim is the name of the package, and I want to run a specific program in Turtle Sim which is called the Turtle Sim node. Turtle Sim underscore node. So what I do, I run this command. So something pops up on the screen. So before I show you what pops up, I'll show you what this is doing. So this saying something called starting Turtle Sim node, name called Turtle Sim. So it is starting, so the ROS is starting to run a node called /Turtle Sim, and what it is doing is it is deploying a turtle called turtle1 at this x coordinate, at this y coordinate, and some orientation. So what exactly is, how exactly is it going to look like? One second, I'll just show you so that I can do it. I hope it is visible. So I'm running the ROS, I am running my ROS commands here on this terminal, and this is something which is created when I give this command called ROS run. One second. Yeah, so I give this thing called ROS run turtle sim sound. So this is what gets deployed. So now what I'm going to do is I'm going to run another node. So what I'm going to run is called turtle teleop key. So I'll just write it down, ROS run turtle sim, again ROS run, name of the package, and then I'm going to run a node which is called turtle underscore teleop underscore key. Okay, so it says reading from keyboard. So what does this thing called turtle teleop key do? So this is basically a C++ or a Python program which will take input commands from my keyboard arrow keys and it will move the turtle in that direction. So I'll show you how it is doing that. So I have my turtle sim here, I have my terminal here. So if you can see, I am pressing my arrow keys right now. If it is visible, I am pressing my arrow keys, and if you can also see, the turtle is moving. So when I am pressing forward, it is going forward, and when I am pressing right and left arrow keys, it is changing its orientation and it's moving in that direction. So this is basically just a demonstration of how the ROS, how turtle sim works, but the working behind it and what exactly happens behind the scenes is something which we can learn about in later sessions. So in case you want to do, we'll do that later, but again I want to show you something else as well. So let me just quickly run one more command and I'll show you the visualization tools in this. So ROS launch, one sec, I think screen is not shared. So I'm keeping my ROS master running because I want to run my ROS commands. So ROS launch, again this is another command which we'll use, turtlebot3. So turtlebot3 is like a pre-built robot, and it has a few functionalities which is created by like the people in the open source community. So what they do is they've created some pre-installed nodes, and they've created some pre-installed simulation environments in which you can test this robot in. So I'll show you something using turtlebot3. So turtlebot3 gazebo is the simulation environment that we're going to use. But before I do this, let me set my one second. So I need to set what type of turtlebot I'm going to be using. So I'm going to do that. So I'm going to use export turtlebot3 underscore model, turtlebot3 underscore model is equal to burger. So this is the name of a turtlebot3 model. So I'm going to be using this model in our simulation environment. So I set it to turtlebot3 underscore model is equal to burger. Run perfectly fine. Now we are going to do something called ROS launch. So what ROS launch does is basically, you saw how we had to run multiple nodes in the previous simulation, in the previous example. I had to open a new terminal, so that I can run a new node every single time. But what ROS launch or creating a launch file can do is you put in all the nodes that you want to run in a launch file, and when you launch this ROS launch, it will automatically run all those nodes in one single terminal. So as I said, we'll get into the details later, but I'll just show you how it works. So turtlebot3 underscore gazebo and turtlebot3 underscore world dot launch. So what I'm doing here, using ROS launch, then I'm using my package which is called turtlebot3 underscore gazebo. So this is the package that I'm going to use, and in that package I'm going to launch something which is named as turtlebot3 underscore world. So once I do this, just a second, I'm facing some issue, but one sec. Oh, one sec. Okay, there's some error. I'll get back. I mean, I'll show you maybe maybe next time. But as you say, as I showed you in the slides, this is what it usually looks like, the gazebo and the RViz environment. This is what it usually looks like. And if that's pretty much it from my side. So if you have any questions, you can shoot your questions. You can ask them in the chat, or you can unmute and ask. Or if that's it, then thank you from my side. And hope it was all useful and you got some idea about ROS. And if you want to know further, then do just let us know. We'll have more sessions on this, or you can talk to me personally also. Thank you. So I guess that's pretty much it.